Hi and welcome to Maths class. Today we're looking at stationary points and particularly how we can use the derivative to learn more about a stationary point on a graph. This can be really useful when we're trying to sketch a graph that's unfamiliar. So first, just a note that a stationary point is a point on the curve with a horizontal gradient. That means it has a derivative of 0. So when you see stationary, that means your gradient is 0, and that's all you need to know straight away. So we have some different types of stationary points. The first one is a local minimum. Now in the past we've dealt with minimums and maximums. A local minimum is a point where the graph dips down and up. Now it may later head back down again. So this may not be the lowest point on the graph, but it is a point on the graph where we have a derivative of 0. So if x equals a at this point, then f dash of a equals 0. Now we know it's a local minimum if to the left of our point, just to the left, we have a negative derivative, and just to the right, we have a positive derivative. That means the graph is coming down when it has a negative gradient and going up when it has a positive gradient. Now we look at the local maximum. It's the same kind of deal. It has a derivative of 0 right on that point where x equals a. So f dash of a is going to equal 0. Then it has f dash of x is positive just to the left of the point and negative just to the right of the point, which basically means it comes up and then it goes down. Now we have one other kind, and that's a stationary point of inflection. And there are two kinds, one basically that has a positive gradient to the left and right, or one with a negative gradient to the left and right. I haven't quite drawn this very well. This is meant to be temporarily a horizontal gradient. It looks more horizontal in this graph here. So same deal. On the point itself, we can see that we have a derivative of 0. With my positive stationary point of inflection, the gradient is positive to the left and right. And with my negative stationary point of inflection, it's negative to the left and to the right. So here the graph comes up, turns right and then goes up. Here it goes down and then turns and comes down. Now, I want to talk just for another moment about points of inflection. A point of inflection is basically a point where the curve stops being concave down, just here, and changes into being concave up. So concave down and up talks about whether my gradient itself is decreasing or increasing. All right, so just think of it as a bowl that's upside down, that's concave down, a bowl that's the right way up, that's concave up. And the point at which that changes, that's our point of inflection. It's only a stationary point of inflection if it has a 0 gradient at this point. Not all points of inflection are stationary. So here, maybe I should have drawn it a bit more clearly. This is concave down here, and then somewhere about here, my graph turns and starts being concave up. I have a point of inflection on this graph, but I don't have a 0 gradient, which means this is not a stationary point of inflection, right? It's a point of inflection. It's not stationary, so it's not one of the things we're looking at today. Today, we're only looking at stationary points. Local minima, local maxima, and stationary points of inflection. So let's do an example just to find my stationary points. Here's my equation. Y equals 2x cubed minus 9 over 2x squared minus 6x plus 3. So to find my stationary points, I need to find the derivative and find out when it's equal to 0. So my derivative, this is a polynomial, so this is not too hard. dy dx, 2x cubed is going to give me the 3 times the 2, that's the 6x squared. Keep my subtraction, 9 over 2x squared, that 2 comes out the front, it's going to become minus 9x and minus 6. So I've got a quadratic equation. Now this one is factorizable. I can see that I've got a common factor of 3, and I'm going to have 2x squared minus 3x minus 2. And so if I factorize that, I'm going to have a 2x times an x, and somewhere I'm going to have a 2, so that's going to be a -2 and a +1. That gives me -4 plus 1 gives me the -3, and the +1 minus 2, that gives me the -2. Okay, so to find my stationary points, this needs to be 0. So let dy dx equals 0 for stationary points. So I get 0 equals 3 times 2x plus 1 times x minus 2, which gives me x equals -1/2, or x equals 2. All right, now go back to the question. The question has a note here that x needs to be positive, and I'll be perfectly honest with you, I popped that in there so that I didn't have to deal with this. Let's just do the x equals 2. So when x equals 2, we're going to have y is going to be 2 times times 2 cubed minus 9 over 2 times 4 minus 6 times 2 plus 3. If I had my CAS, I would grab that, but let's just pretend that I don't. This is 2 8s is 16 minus 18 minus 12 plus 3. So I'm going to have -14 plus 3 is -11. So my point is to -11. Now, oh, sorry, you couldn't see that. My point is 2 at -11. So just to recap, I was asked to find the stationary points. I was asked to do it only for positive values of x. To find stationary points, I need to first find the derivative and then make it equal to 0, which is why I did this factorizing. If I need to solve this derivative for being equal to 0, it's a quadratic. I need to factorize it in order to find the values when x equals 0. I found 2 such values. One was negative, and I only needed positive. So when x equals 2, I just substituted 2 into the original equation, and I found a value of -11. That means that at the point to -11, I have a stationary point on the graph. I don't know what kind it is. I haven't explored that. That's what we're going to look at next. Okay, so this is how we do that. I use what's called a gradient table to help identify the nature of stationary points. Actually, I'm going to pause. I'm going to stop here and I'm going to start a new video to do that.